Welcome back. Today we are continuing our exploration of curve fitting. In the first part, we looked at linear and polynomial models. Now we are moving into the more complex, but very common, territory of nonlinear physics models using the SciPy library. By the end of this session, you will be able to define custom nonlinear functions and use the curve_fit tool to estimate physical parameters. We will also dive into interpreting the mathematical outputs, like POPT and PCOV, and learn how to use residual plots to verify if your model actually makes sense. Just as a reminder, curve fitting is about finding the best parameters to make a mathematical model match experimental data. However, as we discussed in part 1, a visually good fit is not always a physically correct one. To get started, we are importing NumPy, matplotlib, and the curve_fit function from SciPy's Optimize module. Most physics laws are not just straight lines. Whether it is radioactive decay, cooling objects, or damped oscillations, these models are nonlinear. The standard workflow in Python involves defining your model as a function, providing your data arrays, and then calling curve_fit with an initial guess to find the optimal parameters and their uncertainties. Our first example is exponential decay, described by the formula n of t equals n0 times e to the power of negative lambda t. Physically, n0 represents our starting count, and lambda is the decay constant, which determines how fast the system settles. Before we fit real data, let us create some synthetic data where we know the truth. Here we define our decay function and set our true parameters to 100 and 0.42. We then add some random Gaussian noise to simulate the imperfections of a real-world experiment. When we plot this, you can see the blue dots representing our measured count rate over time. The dashed line shows the true underlying physics. Notice how the noise makes the points scatter. Our goal is to see if our fitting algorithm can recover those original true values. Now we perform the fit. The curve_fit function returns two main arrays, POPT, which are the optimal values for our parameters, and PCOV, the covariance matrix. By taking the square root of the diagonal elements of this matrix, we calculate the standard error, or the uncertainty, for each parameter. In this code block, we provide an initial guess of 90 and 0.3. It is good practice to provide guesses that are in the right ballpark. We then extract the fitted values and their errors to see how close we got to our original true inputs. Looking at the output, the algorithm did an excellent job. It estimated n0 at 99.3 and lambda at 0.41, which are very close to our true values of 100 and 0.42. The covariance matrix shows us how these uncertainties are mathematically related. To visualize the result, we generate a smooth set of time values and calculate the model's prediction using our new fitted parameters. We then use matplotlib to overlay this resulting curve on top of our original noisy data points. As you can see in this plot, the solid blue line represents our calculated fit. It passes smoothly through the center of the noise, effectively learning the physics of the decay process from the scattered data points we provided. Mathematically, these parameters give us physical insights. A larger lambda indicates a faster decay, while the reciprocal of lambda gives us the characteristic decay time, often called tau. Remember, even if the uncertainty is small, we still need to ensure the model itself is appropriate for the data. In this specific case, our calculated characteristic decay time is approximately 2.44 seconds. This gives us a single number that summarizes the temporal scale of the entire physical process. To check if our fit is truly good, we look at residuals, which are simply the differences between the data and the model. If the model is correct, these residuals should look like random noise. If you see a specific shape or pattern in the residuals, it usually means your model is missing some physics. We can also quantify the goodness of fit. Here we calculate the sum of squared residuals and the r-squared value. R-squared measures how much of the variance in the data is explained by our model, with a value of 1 being a perfect match. Our R-squared is 0.989, which is very high. This confirms that our exponential model explains nearly 99% of the variation in our synthetic count rate data. A number like R-squared is not enough on its own, so we always plot the residuals. We use a scatter plot and add a horizontal line at 0 to see how the errors are distributed relative to the model prediction. In this residual plot, the points are scattered randomly above and below the 0 line. There is no obvious curve or trend, which is exactly what we want to see. It confirms that our noise was indeed random, and our exponential model was the correct choice. A word of caution: do not over-rely on R-squared. While it is a helpful metric, a high value does not guarantee your model is physically sound. Always use your eyes to check the plots, and use your physics knowledge to evaluate the results. Let us move to a second example: Newton's law of cooling. This model has 3 parameters: the surrounding environment temperature, the initial temperature difference A, and the cooling constant K. This is a classic nonlinear relationship found in thermodynamics. Again, we generate synthetic data. We have set the ambient temperature to 25 degrees and an initial boost of 65 degrees. We have also added a bit of noise to make the data more realistic, similar to what you would see using a temperature probe in a lab. The plot shows a clear exponential approach toward the ambient temperature. In the beginning, the temperature drops rapidly because the gradient is high, and then it levels off as it gets closer to 25 degrees. We fit this using the same curve_fit approach. Because there are 3 parameters now, our popped and PCOV arrays will be larger. We provide a starting guess and let the optimizer find the values for the environment, the amplitude, and the rate constant. The output shows that our estimated environmental temperature is about 25.1 degrees, which is very close to our intended value. The uncertainties for all 3 parameters are quite small, suggesting a reliable fit. We follow the same visualization steps as before, plotting the smooth-fitted cooling curve over the simulated data points. This allows us to verify that the model accurately captures the asymptotic behavior of the cooling process. The resulting plot confirms a beautiful fit. The curve captures the initial steep slope and the eventual flattening, proving that the nonlinear optimizer successfully converged on the correct parameters. We will perform one last diagnostic by calculating and plotting the residuals for this cooling data. This step is vital to ensure that we have not introduced any systematic bias in our 3-parameter model. Just like in the decay example, the cooling residuals show a healthy random distribution around 0. This gives us confidence that our parameters represent the actual physical constants of the system. You might wonder why we need initial guesses. For nonlinear problems, the computer uses an iterative process to find the minimum error. If the guess is too far off, the math might get stuck in a local minimum or fail to converge entirely, especially if the data is noisy. Here, we compare a reasonable guess to a less reasonable one. We have wrapped the fit in a try-except block, which is a smart way to handle cases where the fitting algorithm might crash due to bad starting values. In this simple case, the algorithm was robust enough to find the correct answer even with a poor guess. However, for more complex models like oscillations or peaks, your choice of starting parameters will be much more critical. Let us talk about common pitfalls. One major mistake is picking a model that looks like it fits but has no physical basis. You should also be careful with units. Parameters are meaningless if you do not know if your time is in seconds or minutes. And always double-check that you are not treating the statistical error as absolute truth. 2 other big mistakes are ignoring your residuals and extrapolating too far. A model that fits well between 0 and 10 seconds might completely fail at 100 seconds. Always be cautious when predicting behavior outside your original data range. Now it is your turn for some guided practice. Try increasing the noise in the decay model to see how it broadens your uncertainty. Also, Try fitting a straight line to the cooling data. We have provided some code here using polyfit to show you what happens when you choose the wrong model entirely. This code calculates the residuals for that wrong linear model. When we force a straight line onto an exponential curve, the math will give us a result, but the diagnostic plots will tell a different story. Look at this residual plot. Unlike our previous ones, this has a very clear U shape. The model consistently overestimates in the middle and underestimates at the ends. This pattern is a smoking gun, telling you that a linear model is physically incorrect for this data. To summarize, curve fitting is a powerful tool for connecting data to theory. We have seen that SciPy's curve_fit is perfect for nonlinear models. We have learned to interpret the parameter values and their uncertainties, and we have seen why residual plots are our best friend for diagnosing fit quality. Moving forward, always follow this workflow. Plot your data first, choose a model based on physics, check your residuals, and be honest about your uncertainties. Thank you for your attention, and I will see you in the next session.